Go ahead.
Are you all able to see my screen?
Yes, yes.
Okay.
Yes.
Hello, everyone. Good morning. I'm Santosh. I'm working with Walmart Global Tech as a principal engineer. Along with me, I have my colleague and partner, Jayshed. Today, we are going to talk about LEAF project, and we will also demo about traffic mirroring EBF program. Everyone will be curious to know what is LEAF. LEAF stands for Lightweight EBF Application Foundation. And we have acronym it as LEAF because it is based on a eBPF and is extremely lightweight. In this session, we'll start with brief introduction to eBPF and LEAF, followed by an overview of LEAF platform. Our last release highlights, R2 roadmap, traffic mirroring tool, and we will be closing with the demo. Towards the end, we will be taking the Q&A. eBPF runs as a mini VM inside the kernel. It essentially provides a sandbox environment to insert a code into running kernel. Now let's understand this in a little bit more detail. The Linux kernel is a fundamentally event-driven. Applications that are running in user space make system calls to the kernel. A couple of examples of a system calls includes reading and writing from a disk, connecting application, and reading from the sockets. We also have hardware devices like network cards, disk, and USBs. Now, these hardware devices send interrupts to tell the kernel that certain data is ready to process. Example, when packet arrives to the network interface, when data is available for reading on the disk. The kernel which you see in the middle handles all these events. In cases where we would like to extend the kernel's functionality, the traditional approach is to build your custom kernel by writing modules or submitting the patch to upstream and wait for the next kernel release. eBPF presents a new model which allows us to extend the kernel functionality through a simple programs. These programs can be associated with desired kernel events. So they are executed whenever the event happens. For example, we can run an eBPF program when a packet arrives at the network interface or when an application makes a system call to the kernel. So in the way, eBPF programs are to be what plugins are to the proxy or web servers. eBPF has out-of-box integration with low-level network hooks, such as XTP-TC, as well as probing mechanisms such as K-probes, U-probes, and trace points. Now, eBPF also provides a safe and secured way to write efficient eBPF programs and run them in the kernel. The verification step ensures that the eBPF program is safe to run. It validates that the program meets several conditions. For example, it makes sure that the program does not crash, that it always runs to the completion. The just-in-time compilation step translates the generic bytecode of the program into the machine-specific instruction set to optimize the execution speed of the program. This makes eBPF program run as efficient as native compiled kernel code. The popularity of eBPF is rapidly growing. There are more and more eBPF programs being written to solve a wide variety of problems. Several startups are building technology around eBPF, and large technology companies like Facebook, Netflix, and even Microsoft are embracing eBPF to solve large-scale problems. At Walmart, we too embracing eBPF and using it to solve similar problems. A challenge we faced when first adopting eBPF was how to manage and orchestrate multiple eBPF programs on a large scale. We required to run numerous eBPF programs on a given node, and we have thousands of nodes across many DCs in a hybrid cloud environment using multiple cloud providers. Due to the lack of an enterprise-ready solution, we decided to develop our own platform. Leaf provides complete lifecycle management of EVF programs with the help of an advanced control plane that has been written in Go. This control plane orchestrates and composes independent EVF programs across our infrastructure to solve crucial business problems. Our control plane consists of two major components that work together to orchestrate EVF programs. Deployment APIs, which a user calls to generate the configuration data. The configuration data includes which EVF program will run, their execution order, and the configuration arguments for each EVF program. Leaf-D, which runs on each node, it reads the configuration data and manages the execution and monitoring of a EVP program running on the node. In this way, we have a simple APIs that allow user to add, remove, and reorder EVP programs on the fly. Outside of the control plane, we have developed many EVP programs in the EVP package repository that helps us to replace proprietary applications and hardware with the blazing fast EVP code. Together, the control plane and the EVP package repository come together to provide a EVP program as a service model. Now, as we see in the diagram, EVP package repository, this consists of EVP programs, can be external community developed, third-party vendor ones, or the ones the Leaf community developed. We have a Leaf build engine which pulls the EVP programs, compiles them, and integrated with the CI/CD tools like CodeQL. When a user wanted to deploy an EVP program, he can call a Leaf-D API to provide a configuration data. Once Leaf-D reads this new config, it orchestrates the EVP program on that Linux host as per the defined parameters. If the user gives the set of EVP program, then Leaf-D can orchestrate all of them in the same sequence that the user wanted. Executing EVP programs in a sequence is called chaining, and it is one of the most critical operations that Leaf can perform as a platform. The whole workflow is in line with the build once, deploy everywhere philosophy, wherein we would build the deployment package once for any environment, and in this case, which would translate to multiple kernel versions and set the configuration at the deploy time. R1 is the first release that we did after open sourcing the seed code. We've added authentication using MTLS framework to protect our APIs. MTLS stands for Mutual TLS, which means the client and server each verify each other's identities before proceeding actual tasks. It's a zero trust security model framework. We've added granular APIs to add delete EVP programs from the host. Earlier, we had supported one EVP package repository to download, and currently we have enabled EVP programs to download from multiple package repositories. We have also enabled to load from the local file system. Our repository has been added with the new CI/CD capabilities. It's integrated with CodeQL, OpenSS scorecard, dependent bot, and static check tools. As a part of our R2 roadmap, we have EVP of chaining improvement. Chaining here is running multiple EVP programs in a sequence. Kernel provides a single EVP program that can be attached to the network interface for each type, TC and execute. However, sequentially execute multiple EVP programs by having EVP programs called the next EVP programs in the chain. Each EVP program creates a program type map where the FD of the next program to be stored. Next program in the chain writes the program FD to the map of the previous EVP program. A previous EVP program runs, and before finishing, it reads the FD of the next EVP program and pass it to the BPF tail call to switch the context to the next EVP program. Here, loading and updating program FD into the previous program map is achieved by user program of the EBF program. The chaining improvements implement in the phases. This release will be loading and program map updation is executed by libd. This will remove dependency of user program. In the diagram, you see that all the loading, pinning of the program map and updating of the map is managed by the libd. This will be achieved by using Cilium's eBPF Go library. I want to emphasize Leap supports cross-functional platform. In the upcoming roadmap, we are planning to support XTP programs and libd running on Azure Windows. To achieve loading of EBF programs from native Go library, we need to make changes to existing EBF programs in the eBPF package repository. We'll modify existing root and rate limiting EBF programs initially, and rest will be followed. In the scenario of multiple network interfaces running multiple EBF programs in the chain, we want to make persistent map path from the hard-coded to a dynamic map path. It can support to achieve multiple interfaces running same set of EBF programs in the chain. Support BPF core, which stands for compile once, run everywhere. This provides platform-independent format. This makes it easier for developers to build and test on one kernel version and deploy on multiple kernel versions. Now I have my colleague to talk about traffic mirroring and conclude with the demo.
Hello, everyone. My name is Jay Shat, and I am an engineer at Walmart Global Tech. And today I will be talking about a new eBPF-based traffic mirroring tool, or TMT for short, that was open sourced recently. First, let's discuss a few of its features, and then we will have a short demo showing TMT in action. Traffic mirroring is traditionally performed on a physical switch where the network traffic from certain ports is cloned and sent to another machine apart from its destination via different ports. However, in case of cloud infrastructure or in case of network function virtualization, or especially when we have limited access to the physical switch itself, the traffic mirroring functionality is generally implemented in the software. Simply put, the traffic mirroring tool is an eBPF program which is attached to the TC ingress and egress hooks. So when a packet is received or transmitted by the host with a specific BPF helper function, apart from directing the packet to the regular TCP/IP networking stack, the BPF helper function clones the packet and sends it to the collector. Furthermore, not all traffic might be of interest, or we might want to conserve the bandwidth by mirroring only the few packets among the incoming and outgoing packets. Hence, in TMT, filters based on phi tuple can be provided, based on which only the traffic that matches with the filter parameters is mirrored. To further reduce the bandwidth overhead, we are also working on adding a functionality where only the headers of the mirrored packets will be sent to the collector instead of the complete packets with the payload. Next, let's jump into the Leaf development environment. A document enlisting all the required steps can be found in the Leaf ARC repo, which will help in getting started with using libd and traffic mirroring. We can create a dev environment using a native Linux machine or using a Vagrant file to spin off VMs and the required software. This slide presents the main components of Leaf ecosystem, and these components will be installed as a part of the Vagrant file or the shell scripts provided in the GitHub page. First component is the Leaf daemon, shown here as libd, which sits on each of the participating nodes. It is a central entity to all the other components in the ecosystem. For example, we can initiate a command to libd via a REST API to load an eBPF program. It fetches the corresponding binaries from the eBPF package repository and loads the program into the kernel. Once the program is loaded, we can initiate web traffic and then communicate with the web server. Finally, LeafD collects and exports the specified metrics, and we can observe the collected metrics via the Grafana dashboard via our browser. Next, we will see traffic mirroring and LeafD in action. We will have two VMs, one which would be the host and then the other one which would be the collector. We will generate traffic from source, which is our laptop, towards the host, and traffic mirroring program on the host will clone the packets and send it towards the collector via a GUI runner. I have already created two VMs via the vagrant file provided in the Leaf org repo. So here on the screen, we have primarily three windows of interest. The one on the left represents the source or our local computer or laptop. The one on top right is for the host, which will have LeafD and traffic mirroring tool installed on it. And finally, we have the third window, which represents the collector VM or where the mirrored traffic will be destined to. Let's first start the Leaf daemon. Here we can see that the Leaf daemon has started and it's listening on port 7080. Next, we will be sending JSON config payload to this server to instantiate eBPF programs. I have a sample JSON payload over here. Using this config, we will be loading an XTP program called connection limit, which monitors and limits the maximum number of TCP sessions per second. You can refer to the Git repository for more details on connection limit. Simultaneously, we will be loading the traffic mirroring programs for both TC egress and TC ingress. And specifically in case of TMT, the configuration is set such that all the ingress and egress packets with destination port and source port respectively 8080 will be mirrored to the collector. From the source, we can now initiate the post request and send it to LeafD to load the sample config. And as we can see that the post command returned with no errors, hence we can conclude that all the programs were successfully loaded by LeafD. Next, specifically in case of vagrant development environment, we will need to delete the default route added by traffic mirroring tool. With traffic mirroring tool loaded, let's try to send some traffic. First, on the collector, we will run TCP dump and save the output to a PCAP file. Similarly, on the host where we'll be sending the traffic to, we will also run TCP dump and see what packets are captured. Finally, on the source, we will be using the curl command to send an HTTP packet whose payload contained hello leaf in it. Here we can see that the packet sent to the host is received by the host and the TCP dump shows the characteristics and the packets captured. The capture which was collected on the collector, we can see that we have received some HTTP packets, and inside, if we check the payload, we have hello leaf in it. Hence, we can conclude that the traffic which was sent by the source to the host was then mirrored by the traffic mirroring program and then sent it to the collector. Now we can send large amount of HTTP traffic via the hey command. So we will run TCP dump on the collector. Similarly, we will run TCP dump on the host, and then we will be generating HTTP traffic via the hey command. And here we can see that all the traffic which was sent to the host is also mirrored to the collector. Similarly, we can also check out the Grafana dashboards where LeafD is exporting the metrics. So in case of the connection limiting program, we can see there is a huge spike corresponding to the number of connections instantiated by the Hey command. And also in other dashboards, we can check the status of the programs. Also, we would highly encourage you to try out the Leaf development environment, traffic mirroring, and other eBPF programs. And feel free to join our mailing list, Slack channel, and weekly TSC to participate in technical discussions or in case if you have any questions. Thank you everyone for listening this talk, and we will be happy to answer any of your questions.
Okay, thank you so much. I'll go ahead and stop the recording.